Okay, a full curve sketch. So number one, domain. So we're looking at an E function, so I have a domain of all real numbers. Number two, let's look at the intercepts. Okay, so we have x-intercept when y is equal to 0. So is this possible? We were just looking at that one of these with our critical numbers. E to the exponent, any exponent, it's never going to be 0, right? Think about horizontal asymptote. So we have no x-intercept. And then what about a y? So the y-intercept would be when y is, or x is equal to 0. So e to the power of negative 0 squared. So really e to the power of 0, which is 1. So we have this y-intercept, very typical, at 0, 1. Third thing I'm going to look at is symmetry. Okay, so remember when we're doing symmetry, then we're going to replace x with negative x. So what happens in our function when we do that? So we have e, be careful, with the negative, and then we're replacing just the x with negative x squared. So you actually end up with the exact same function. So we have that f of negative x is equal to f of x. And what does that mean? Remember what that means from chapter 5, that we have an even function. So we will be symmetrical on both sides of that y-axis. All right. Number 4, asymptotes. Okay, so we aren't going to have a vertical asymptote because there's no denominator. What about a horizontal? Well, we are suspicious that there is a horizontal because there should be one on an exponential. So remember, in a proper curve sketch, that you would evaluate the limit as x goes to infinity on that. And so this is from our 8.1 lesson. So what happens here when you put in a really big number and square it? Well, it's really big, and then he's negative, right? So this is going to be equal to the limit as x goes to infinity of e to a negative, really big number. Okay, so which is the same as the limit as x goes to infinity over 1 over e to my big number, right? Because that's using my exponent laws. And that's going to go to 0. So therefore, I have a horizontal asymptote at y equals 0. All right, number 5. Got to change up the color. I don't know why I chose black. Whew, boring. Okay, we're going to look at our intervals of increase and decrease. All right, so what do we have? We need to take the derivative of our function. Our function was e to the power of negative x squared. So the derivative of this is e to the same exponent multiplied by the derivative of that exponent, which would be negative 2x. Leave that in factored form because we're going to set this equal to 0 to find the critical number piece next. So we're going to look at e to the power of negative x squared being equal to 0, and we're going to look at negative 2x being equal to 0. And hopefully we've gotten into the knowledge now that the first case is not going to exist. E to any exponent is never going to equal 0. But in the second case, x would be equal to 0. So we have one critical number. Pardon me. So let's test that on our number line. And what are we going to test? How about -1 and +1? I did not mean to just go bigger on that. I meant to change my color. Oh, well, that's okay. Wrong direction. Here we go. Okay, so what does this tell me about the derivative? If I put in a negative, e to the power of anything's going to be positive. So then -2 times -1 is positive. So I have a positive. And then over here, I'm going to get my negative because I'm going to have -2 times +1. And so what does that tell me about my function? Increase, decrease with a max in the middle. And so you would say that we are increasing, if we were doing a really good curve sketch, we are increasing from negative infinity to -1 and decreasing from, oh, sorry, 0. My bad. Let's get that out of there. 0, and then decreasing from 0 to positive infinity. And then what's happening with this max guy? So, oh man, I wanted a different color. Okay, there we go. So what is this max? Max is happening at 0. So what is f of 0? When we put that into our exponent, we have e to the power of 0, because 0 squared times -0. So that's equal to 1. So we have our max happening at our y-intercept at 0, 1. All right, trucking along. Number 7 will be our concavity and our points of inflection. Okay, so let's see. We know that our first derivative is e to the power of -x² times -2x. So to do our second derivative, we are going to need to do the product law. So 1 d2 plus 2 d1. Careful to remember to take the derivative on that chain on that last part. Okay. Okay, so then the best thing to do here is to factor. Now you might feel like it might be better to reorder and tidy up before you decide on who's your GCF. 2 times 2, 4x². And then it's so much easier to find your critical number, or sorry, significant number. We're in second derivative here. So what do we have as a common factor? I see a -2 e to the power of -x². What would I be left with? That would be 1 plus, nope, minus 2x. 1 minus 2x². All right, and we're going to set that equal to 0 to look for those significant numbers. Okay, so we have -2 e to the power of -x² equal to 0, or 1 minus 2x² equal to 0. What's going to happen from here? Again, this guy over here, he's not going to exist. The first case. Second case, we would have 2x² is equal to 1. So x² would be equal to ½ x is going to equal to plus or minus the square root of the 1/2, and some of you may prefer to write that with a rationalized denominator. So plus or minus √2 on 2. And now we're going to put that on our little tester. And so we are going from -infinity to positive infinity, and we have a negative √2 on 2 and a positive √2 on 2. And this will test, I'm going to test -1, 0, and 1. And what does that tell me? So my second derivative, when I put -1 in, I get a positive, and then I get a negative, and then I get a positive. So what does that tell me about my function? It tells me I'm going concave up, concave down, concave up. And we could make ourselves a little statement about that. We are concave up from -infinity to √2 on 2, or from positive √2 on 2 to positive infinity. And we are concave down when we are in between those two. And we also have 2 points of inflection because we have concavity changing right here. So what are those points of inflection? I was just seeing how much room I have. I have to squeeze those points of inflections in right here. Okay, so when I put this in, you have to go e to the power of negative root 2 on 2 squared. And it doesn't matter, you could put your plus and minus in, you could do this at the same time because you're squaring it. So what you get is e to the power of negative a half, which is the same as 1 on square root e. So therefore, those points of inflection are happening at plus or minus root 2 on 2 and 1 on the square root of e. Those are your points of inflection. Sorry, I'm squishing stuff, I know. Okay, and here we go. Last piece then is the actual sketch. Okay. What did we learn as we went through all of this analysis work? We learned that we have a y-intercept at 0, 1. And we have a point of inflection happening, let's say somewhere right about there, I think. Negative root 2 on 2 and 1 on root e. And symmetry, so I'm going to try to make this symmetrical, with similar on the other side. Positive root 2 on 2 and 1 on root e. And when I try to put this all together, oh, I forgot my horizontal asymptote at y is equal to 0. All right, so now we should look like concave up, down, up. And there's our beautiful graph. We succeeded. Remember to label important pieces. You can even label those as max and points of inflections. Those always make your teachers happy when you are like, I know exactly what that point actually means. There we go. We managed to do a curve sketch for an exponential function. All right, last question. We need to find the equation of the normal to this curve. Okay, so remember a normal is a line perpendicular to a line at the point of tangency. Okay, and I only have 2 minutes left, so it's probably better if I just start a new video just so I'm not super rushed. Go ahead and give this question a try all on your own. I think you have all the tools that you need.